Right now, as you lie perfectly still, you are hurtling through space at a speed that is almost impossible to imagine. Your body is spinning along with the Earth around its axis at more than 1,000 miles per hour. Together with the Earth, it is racing around the Sun at nearly 67,000 miles per hour. Together with the solar system, it is moving around the center of the Milky Way at more than 500,000 miles per hour. And the galaxy itself is traveling through intergalactic space at more than 1.2 million miles per hour. You have never, not for a single second, been motionless. Never. The idea of rest is the most persistent, the most natural, and the most mistaken idea in the history of humanity. We believe that doing nothing is the normal state of affairs, that rest is the natural condition and movement is the deviation. But the universe is structured differently, and this misunderstanding, this deep intuitive error, cost us 2,000 years.
Why are we so certain that rest is the natural state?
Why do we believe that any movement requires an explanation, but the absence of movement does not? Where did this conviction come from? A conviction so powerful that it held back the development of science for 20 centuries. And how did we manage to break it? Because what you feel as stillness is simply one of many perspectives. It is an illusion created by friction, by air, and by our limited perception. And physics, real physics, began exactly at the moment when someone decided to ask, "What if I am wrong?" Let us try to imagine a world where everything would be clear at first glance. A world where you do not need to ask complex questions because the answers lie on the surface. You see a stone fall to the ground. You see smoke rise upward. You see water flow down a slope. You see that if you push a cart, it will travel a little and then stop. All of this seems natural. It does not require explanations.
It is simply how things are. This is what not one person thought. This is what all people thought for thousands of years. And in this lay the greatest mistake humanity has ever made. The man who created this system of explanations lived in Greece in the 4th century before the Common Era. His name was Aristotle. He was a student of Plato and a teacher of Alexander the Great. He wrote books about everything imaginable, about logic, about politics, about poetry, about animals, about the soul, about the state, and of course, about physics. His book about the nature of things was simply called Physics, and in it, he gave people an explanation of the world that seemed flawless. He explained why things move exactly as they do and not otherwise. And this explanation was so convincing that it was accepted without criticism for 2,000 years. At the heart of his theory lay the idea of natural places. Aristotle believed that everything in the world has its own proper place in the universe. There are 4 basic elements: earth, water, air, and fire. Each of these elements has its own natural position. Earth sits at the center of everything, at the very bottom. Water sits above the earth. Air sits above the water. And fire sits above everything, rising toward the celestial sphere. It was a beautiful, orderly hierarchy. When you throw a stone, it falls to the ground because it is made of the element earth and wants to return home, to its natural place. When you light a fire, the smoke and flames rise upward because they contain the elements air and fire, which strive toward their places in the upper reaches of the universe. It is simple, it is logical, and it matches everything we see every day. Aristotle also explained why some things move while others remain at rest. He divided all motion into 2 types. Natural motion is what happens on its own,
without any external influence. A stone falls downward. That is its nature. Smoke rises upward. That is its nature. Fire strives upward. That is its nature. No external force is required. The object simply follows its inner essence. But there is also another kind of motion, violent motion. This is motion that happens when some external force acts on an object. You push a cart and it moves. You stop pushing and it stops. You throw a stone and it flies in an arc until it falls. You pull a boat and it moves through the water. In all of these cases, motion requires constant pushing. If the force stops acting, the motion stops. This seemed absolutely obvious. Anyone who had ever pushed a cart or pulled a wagon knew this from their own experience. And here we come to the most important, the most insidious, and the longest-lasting error in the history of science. Aristotle believed that for an object to keep moving, a force must constantly act upon it. If the force stops acting, the object stops.
This is not just an assumption. This is a law. It was so natural that no one doubted it for 2,000 years. 2,000 years. That is almost as long as the time that separates us from the birth of Christ to the present day. An entire epoch. Why did this error last so long? Because in ordinary life, this is exactly what we see. If you stop pushing a box across the floor, it stops. If a horse stops pulling a wagon, it stops. If you stop rowing, the boat stops. If you throw a ball into the air, it will fly a little and then fall. No one had ever seen an object that kept moving forever without any external influence. This contradicted all human experience. Imagine how difficult it was to notice the error when everything around you confirmed that you were right. The error was hidden behind everydayness. It was hidden behind what we call common sense. But there was one small nuance, one detail that did not fit into this perfect picture: the arrow. When an archer releases an arrow from the bow, it keeps flying. The archer's hand no longer touches the arrow. The bowstring no longer pushes it. The arrow has already left the bow, but it is still moving. How can this be explained according to Aristotle? After all, if motion requires a constant force, then who or what is pushing the arrow after it has left the bow? This question should have made any thinking person pause. And Aristotle, being a brilliant thinker, did not leave it unanswered. He found a clever explanation. He said that the arrow is pushed by the air. When the arrow flies forward, it creates a rarefaction behind it, a kind of vacuum, and the air surrounding the arrow rushes forward to fill this void. In its movement, the air pushes the arrow from behind, sustaining its flight. This was a complex but logical explanation. It saved the theory. It showed that Aristotle had accounted for everything. He had thought of what is invisible to the eye. He had created a complete system with no gaps. It was brilliant. And it was absolutely wrong. But no one could test it. To see that the air does not push the arrow, you had to imagine a world without air. A world without resistance. A world where an object, given one push, would move forever. Such a world did not exist in nature. It had to be imagined. And imagination was not prized in science. In science, you had to follow the authorities. And the authority was Aristotle. Imagine this prison, the prison of common sense. A world that is understandable, logical, and comfortable. In this world, rest reigns, and motion is the exception that must be constantly maintained. This idea was so convenient that it was accepted without criticism for almost 2,000 years. In that time, the Roman Empire fell. In that time, the Byzantine Empire rose and fell. In that time, Gothic cathedrals were built, and the Crusades began and ended. In that time, dozens of generations came and went, and all this time people lived with this idea. They built cities, waged wars, created empires, and no one doubted how the world was structured. Physics was not a science but a philosophy. It was not an investigation, but a confirmation of what the great sage had said. It was a path to nowhere. But even in the darkest times, there were people who doubted. They saw that the arrow kept flying. They felt that the explanation with air was too complex and unconvincing. They noticed that heavy objects fell faster than light ones, but not always. They noticed that in water, heavy objects fell more slowly than in air. They sensed that somewhere there was a crack in this perfect wall, and they began to look for this crack. It took them almost 2,000 years to find it. It took a man who dared to say, "I do not believe in words, I believe in my own eyes." A man who decided to test what seemed obvious. A man who looked at the world as if he was seeing it for the first time.
That man was Galileo Galilei. But before him, there were others. In the Islamic world, during the Golden Age, scholars did not merely preserve the works of Aristotle. They studied them, commented on them, and sometimes questioned them. They asked questions that Aristotle had not asked. They conducted experiments that Aristotle had not conducted. They approached the truth without even knowing it. One of them, Ibn Sina, known in the West as Avicenna, proposed an idea that was one step closer to the truth than Aristotle's explanation. He said that a thrown object receives from the push a certain force, which then gradually weakens. This is not quite inertia, but it is no longer air. It is already an acknowledgement that motion can be an internal property of an object. Another thinker, Buridan, who lived in Paris in the 14th century, went even further. He called this internal force impetus. He said that when you throw a stone, you transfer impetus to it, and this impetus makes the stone move until it is exhausted. The impetus weakens due to air resistance and due to the action of gravity. This was a brilliant guess. It was very close to the truth. Buridan understood that motion does not require a constant external force. He understood that motion can be the result of an internal property of an object. He made a huge step forward. But he still did not see the full picture. He did not understand that in a world without resistance, the impetus would never be exhausted. He could not imagine a world without friction, without air, without resistance. His world was still Aristotle's world, but already with cracks, and these cracks were growing wider. Several more centuries passed, and the Renaissance arrived. Europe was awakening from a long sleep. People again began to take an interest in science, art, philosophy. They began to read the ancient authors not to confirm their words, but to understand them. And they began to notice that Aristotle was not always right. They began to notice that the world was more complex than it seemed. And then Galileo appeared. He was born in Pisa in 1564. He was a mathematician, a physicist, an astronomer, and an engineer. He was one of the most brilliant minds of his time, and he decided to settle the question of motion once and for all. He did not read Aristotle. He did not comment on him. He decided to test his words in practice. Galileo took 2 balls of different weights and, according to legend, dropped them from the Leaning Tower of Pisa. The legend says that he wanted to show that heavy objects do not fall faster than light ones. In reality, he most likely did not drop balls from the tower, but he conducted other experiments. He used inclined planes. He slowed down the fall so it could be measured. He used his pulse to measure time. He was patient and methodical, and he discovered an amazing thing.
If you remove all obstacles,
if you remove friction and air resistance, then all objects move the same way. A light ball and a heavy ball accelerate equally. They fall at the same speed. This contradicted everything Aristotle had said. This contradicted everything that seemed obvious. Galileo went further. He began to think about what happens when an object moves on a perfectly smooth surface. He imagined a ball rolling on a perfectly level and smooth floor. What would happen to this ball? Aristotle would say that it would stop because the force had ceased to act. But Galileo thought differently. He said, if there is no friction, if there is no resistance, then the ball will roll forever. It does not need a force to keep moving. It needs a force to stop. This was a revolution. This was the complete destruction of the Aristotelian world. Galileo understood that rest is not the natural state. The natural state is motion. An object moves because it was moving. For stopping, there needs to be a reason. For changing motion, there needs to be a reason. But for motion itself, no reason is needed. This idea was so radical that Galileo's contemporaries could not accept it. They were accustomed to a different world. They were accustomed to the idea that motion requires a constant force. They were accustomed to the idea that rest is the norm. They could not imagine a world without friction. They could not imagine a ball that rolls forever. This contradicted their experience. But Galileo was right, and he knew it. He knew that the world was structured differently than it appeared. He knew that our senses deceive us. He knew that to understand the truth, you have to look deeper. You have to remove the interference. You have to imagine ideal conditions. You have to trust not what you see, but what you can calculate. Galileo showed that motion is the natural state. He turned the world upside down. But he could not explain why. He could not explain why some motions look one way and others another. He gave us the key, but he did not show which door it opened. He showed that Aristotle was wrong, but he could not provide a complete alternative. He could not explain why planets move in orbits. He could not explain why the moon does not fall to Earth. He could not explain why an apple falls downward and not sideways. He left these questions for others. He left them for a man who was born in the year of his death. A man who completed what Galileo had begun. A man who created the universal law of motion. A man who showed that the same force governs both the fall of an apple and the motion of the moon. The next chapter of this story is about the man who united the heavenly and the earthly. About the man who understood that the universe is a single mechanism, operating according to single laws. About the man who began where Galileo left off. Galileo died in 1642. In that same year, according to the Old English calendar, in a small village in Lincolnshire, a boy was born. He was so weak and so small that his mother said he would have fit inside a quart mug. They named him Isaac Newton. He was born on Christmas Day, the very day the world lost Galileo. History loves such coincidences. One great man departs, and another takes his place, as if a baton is passed through death and birth. Galileo had shown the way, but he had not reached the end. Newton was to walk that path all the way to the finish. He was to build the structure whose foundation Galileo had laid. He was to create a science of motion that would stand unchanged for nearly 300 years. But before we turn to Newton, let us go back to those who prepared the ground for this revolution. Because between Galileo and Newton, there were several more decades. Decades during which Galileo's ideas spread across Europe. Decades during which people learned to think in new ways.
Decades that prepared the soil for Newton to make his great breakthrough. In the middle of the 17th century, Europe was seized by intellectual ferment. Old ideas were dying, new ones were being born. People began to doubt authorities. People began to trust their own eyes and their own reason. This was the age of the scientific revolution, the age when the foundations of modern science were laid. In England, in 1660, the Royal Society was founded. It was a community of scientists who gathered together to discuss their ideas and share the results of their experiments. It was a place where the new science was being born. The members of the Royal Society were obsessed with the idea of experiment. They did not want to just read books. They wanted to test things. They wanted to see with their own eyes. They wanted to measure. This was a new philosophy. A philosophy based not on authority but on experience.
One of the first great scientists who worked in this new spirit was Robert Hooke. He was a contemporary of Newton and his chief rival. Hooke was a genius in many fields. He was an architect, a biologist, a physicist, an inventor. He built one of the first microscopes and saw a world that no one before him had ever seen. He saw cells. He saw the structure of plants. He saw a world hidden from the naked eye. Hooke also worked on physics. He studied motion. He studied elasticity. He studied force. And he came to a conclusion that was close to the idea of inertia. He understood that force is needed to change motion. He understood that without force, an object would move uniformly. But he could not formulate this clearly. He could not create a theory that would unite all observations. That was left for Newton. But before Newton, there was another great mind, René Descartes. He was a French philosopher and mathematician. He lived in Holland, far from the censorship of the Catholic Church.
And he created a new philosophy that became the foundation for all modern science. Descartes said, "I think, therefore I am." This was a simple but powerful argument. It asserted that the only thing we can be certain of is our own consciousness. Everything else might be an illusion. We must build knowledge on the basis of doubt. Descartes also created a new physics. He discarded Aristotle's ideas about natural places. He said that the world consists of matter moving through space. There are no purposes for objects. There are no natural places. There is only matter and motion. And motion obeys laws. Descartes formulated his own law of inertia. He said that an object will continue to move in a straight line until some force acts on it. This was a huge step forward. But Descartes made one mistake. He said that an object will move in a straight line until it encounters an obstacle. He did not account for the fact that in a world without obstacles, an object would move forever.
He did not account for the fact that motion requires no cause. He was still looking for a cause for motion. He still thought that motion must have an explanation. This was the last error on the path to truth. Descartes was close, but he did not reach the end. He left this task for Newton. Isaac Newton was born in 1642. His father died a few months before his birth. His mother remarried when he was 3 years old and left him in the care of his grandmother. Newton grew up as a withdrawn and lonely child. He did not like people. He did not like society. He loved only books and experiments. He was obsessed with the idea of knowledge. He wanted to know how the world worked. He wanted to know why things moved exactly as they did and not otherwise. He wanted to know the laws that govern the universe. In 1661, Newton entered Cambridge University. He was a poor student, and he had to earn his living by serving the wealthier students.
He was not an outstanding student. He did not shine in lectures. But he read widely. He read Descartes, he read Galileo, he read Kepler. He read everyone who wrote about motion and about the heavenly bodies. And he began to ask questions that no one could answer. In 1665, the plague struck England. It was a terrible disease that claimed thousands of lives. Cambridge University closed. The students scattered to their homes. Newton returned to his native village of Woolsthorpe, to his mother's house. He was 23 years old. He was alone. He was isolated from the world. He had time to think. And in this seclusion, in the silence of the English countryside, Newton made his greatest discoveries. He began to think about motion. He began to think about force. He began to think about gravity. Legend has it that one day he was sitting in the garden and saw a falling apple. And this simple, ordinary moment made him wonder, why does the apple fall downward? Why does it not fall sideways? Why does it not rise upward? Why does everything fall downward? What makes objects fall to the earth? Newton realized that the answer must lie in some force, a force that pulls objects toward the earth. But he went further. He asked himself, what if this force does not act only on Earth? What if this force acts in space as well? What if the very same force that makes an apple fall also makes the moon orbit the Earth? What if one and the same force governs both the fall of an apple and the motion of the planets? This was a brilliant insight. It was a breakthrough that changed everything. Newton understood that the laws of motion are the same for the entire universe. There is no difference between the earthly and the heavenly. There are no natural places for different elements. There is only one force. There is only one law. And this law acts everywhere, from an apple to a planet. Newton began to calculate. He knew that the moon orbits the Earth.
He knew that the Earth orbits the Sun. He knew the distances and the speeds. He began to calculate what force was needed to keep the moon in orbit, and he discovered that this force obeyed a simple law. The force of attraction decreases with the square of the distance. If the distance doubles, the force decreases by a factor of 4. If the distance triples, the force decreases by a factor of 9. This was the inverse square law. It was simple, elegant, and universal. Newton did not publish his discoveries immediately. He was cautious. He feared criticism. He knew that his ideas were too radical. He knew that people were not ready for them. He hid his calculations in a desk drawer and forgot about them for almost 20 years. He occupied himself with other things. He studied alchemy. He studied theology. He studied history. He was not only a scientist, he was a man who sought truth in all its manifestations. He was a man who believed that the world was one and that all its parts were connected. In 1684, in London, 3 scientists met: Edmund Halley, Robert Hooke, and Christopher Wren. They were discussing the problem of planetary motion. They knew that planets move in elliptical orbits, but they did not know why. They did not know what force made them move that way. Hooke claimed that he knew the answer. He said that the force of attraction decreases with the square of the distance, but he could not prove it. He could not derive it mathematically. Wren offered a prize to anyone who could solve this problem. Halley decided to turn to Newton. Halley travelled to Cambridge and met with Newton.
He asked him, "If the force of attraction decreases with the square of the distance, what trajectory will a planet follow?" Newton answered immediately, "An ellipse." Halley was stunned. He asked how Newton knew. Newton said that he had calculated it many years earlier.
Halley asked Newton to show his calculations. Newton rummaged through his papers but could not find them. He promised to recalculate and send the result. A few months later, Halley received a short treatise from Newton. In it, Newton laid out his laws of motion and the law of universal gravitation. It was a draft of his future masterpiece. Halley was so impressed that he decided to publish it. He even offered to pay for the printing out of his own pocket. Thus began the work on the mathematical principles of natural philosophy, the book that would change the world. Newton worked on it with tremendous intensity. He barely slept, he barely ate. He was consumed by his work. He wanted to create a complete and consistent theory of motion. He wanted to show that all natural phenomena obey the same laws. He wanted to show that the universe is a single mechanism, operating according to a single set of rules. Finally, in 1687, the book was published. It was called Philosophiae Naturalis Principia Mathematica, which translates as the mathematical principles of natural philosophy. It was one of the most important books in the history of humanity. It contained 3 laws of motion and the law of universal gravitation. 3 laws that explained everything, from the fall of an apple to the motion of the planets. Newton's first law stated, "An object remains at rest or in uniform motion in a straight line unless acted upon by an external force." This was the law of inertia. This was the law that Galileo had formulated in general terms, but Newton gave it precise mathematical form. He showed that motion is the natural state. It does not require an explanation. Change in motion requires an explanation. Force requires an explanation. Newton's second law stated, "The change in motion is proportional to the applied force and occurs in the direction of that force." This was the law that connected force, mass, and acceleration.
It showed that force is the cause of change in motion. It showed that mass is a measure of resistance to change in motion. It gave us a tool for calculating motion. If we know the force and the mass, we can calculate the acceleration. If we know the acceleration, we can calculate the speed and position. We can predict the future. Newton's third law stated action equals reaction. This was the law that showed that forces always come in pairs. If object A acts on object B with some force, then object B acts on object A with exactly the same force but in the opposite direction. This was the law that explained why we can walk on the ground. We push off from the ground and the ground pushes us back. This was the law that explained why rockets fly. A rocket expels gas backward and the gas pushes the rocket forward. And then Newton formulated the law of universal gravitation.
He said that any 2 bodies attract each other with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This was a simple, elegant, and universal law. It explained why an apple falls to the ground. It explained why the moon orbits the Earth. It explained why the Earth orbits the Sun. It explained why the planets move in elliptical orbits. It explained the tides. It explained the shape of the Earth. It explained everything. Newton showed that the same force governs the fall of an apple and the motion of the planets. He showed that the universe is a single mechanism, operating according to single laws.
He showed that there is no difference between the earthly and the heavenly. There are no natural places for different elements. There is only one force. There is only one law. And this law acts everywhere, from an apple to a planet. It was a triumph of the human mind. It was proof that the world is knowable. It was the beginning of a new era in the history of science. But Newton did not answer one question. He did not say what gravity is. He did not say how it works. He did not say why it exists. He said only how it acts. He gave us a formula, he gave us a law, but he did not give us an explanation. He did not know what gravity was, he knew only that it existed. Newton himself admitted this. He wrote, "I frame no hypotheses." He did not want to guess. He did not want to speculate. He wanted only to describe facts. He wanted to give us a mathematical model that works, and he gave it to us. It worked for nearly 300 years. It worked until a man appeared who asked the question, what if time is not absolute? What if space is not absolute? What if everything is relative? This question led to a new revolution, a revolution that changed our understanding of the universe, a revolution that showed that even Newtonian physics is not the final truth. It is only an approximation that works in most cases, but that fails at the boundaries of knowledge. But we will not rush ahead, because the story of motion does not end here. In fact, it is only beginning. Newton gave us a tool. He gave us laws, but he did not give us understanding. He did not tell us why gravity exists. He did not tell us what space and time are. He did not tell us how the universe is really structured. These questions remained for others, for those who came after Newton, for those who continued his work, for those who asked new questions and found new answers. In the next chapter, we will see how these new questions led to new discoveries, how people began to understand that space and time are not absolute, how they began to understand that gravity is not a force, but a curvature of space-time, how they began to understand that the universe is much more complex than Newton thought. But that will be in the next chapter. For now, let us pause on what Newton did. He united the heavenly and the earthly. He showed that the same force governs the fall of an apple and the motion of the planets. He created a theory that worked for nearly 300 years. He gave us a tool for understanding the world. And he left us a question for the generations to come. What is gravity? What is space? What is time? And the answer to this question came from a man who was born 200 years after Newton. A man who sat in a patent office in Bern and thought about what would happen if you traveled at the speed of light. A man who showed that time is not absolute. A man who showed that space is not absolute. A man who showed that gravity is not a force, but a curvature of space-time. That man's name was Albert Einstein. He was born in 1879. He was the son of an engineer. He studied at the Zurich Polytechnic. He worked in a patent office. He was not wealthy, not famous, and not known. But he was a genius. He asked questions that no one else asked. He found answers that no one else sought. He changed our understanding of the universe. But that will be in the next chapter. For now, let us simply remember that Newton gave us the foundation. He gave us laws that work in everyday life. He gave us a tool for understanding the world. He showed that the universe is a single mechanism, operating according to single laws. And he left us a question for the generations to come. In the next chapter, we will see how the next great mind, Einstein, answered this question. We will see how he overturned our understanding of space and time. We will see how he showed that gravity is not a force, but a curvature of space-time. We will see how he created a new theory that replaced Newton's, but that will be in the next chapter. For now, let us simply rest and think about how far we have come. From Aristotle to Newton. From faith in authorities to trust in experiment.
From the idea of natural places to the idea of a single force governing the entire universe, we have come a long way. And ahead of us lies an even longer road. A road that will lead us to understand that the universe is much more complex than we thought. A road that will lead us to understand that time and space are not absolute. A road that will lead us to understand that gravity is not a force, but a curvature of space-time. A road that will lead us to understand that the universe is not a machine, but a dance. A dance in which we all participate, without even knowing it. Newton created a system that worked. It worked so well that for nearly 300 years, no one could find a flaw in it. It explained the fall of an apple and the motion of the planets. It explained the tides. It explained the shape of the Earth and the trajectory of comets. It was universal. It was precise. And it was simple. 3 laws of motion and 1 law of universal gravitation. Just 4 statements. And they explained everything. The first law: an object remains at rest or moves uniformly in a straight line unless acted upon by a force. This is the law of inertia. This is the very law that Galileo had formulated in general terms, but Newton gave it precise mathematical form. It tells us that motion does not require an explanation. Change in motion requires an explanation. If you see an object moving at constant speed in a straight line, you know that no force is acting on it. If you see an object speeding up, slowing down, or changing direction, you know that a force is acting on it. The second law: force equals mass times acceleration. This is the law that connects force, mass, and motion. It tells us that the greater the mass of an object, the more force is needed to change its motion. It tells us that acceleration is directly proportional to force and inversely proportional to mass. This is the law that allows us to calculate motion. If we know the force and the mass, we can calculate the acceleration. If we know the acceleration, we can calculate the speed and position. We can predict the future. The third law: action equals reaction. This is the law that tells us that forces always come in pairs. If object A acts on object B with some force, then object B acts on object A with exactly the same force, but in the opposite direction. This is the law that explains why we can walk, why we can swim, why we can fly. The law of universal gravitation. Any 2 bodies attract each other with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This is the law that explains everything. It explains why an apple falls to the ground. It explains why the moon orbits the Earth. It explains why the Earth orbits the Sun. It explains why the planets move in elliptical orbits. It explains the tides. It explains the shape of the Earth. It explains everything. These 4 laws became the foundation of classical physics. They worked. They worked so well that it seemed we had found the final truth. It seemed we had understood how the world was structured. It seemed we had reached the limit of knowledge. But Newton knew that this was not the case. He knew that his theory was incomplete. He knew that it did not explain what gravity is. He knew that it did not explain how gravity acts across a distance. He knew that it did not explain why gravity exists. He knew that his theory was only a description of how the world works, but not of why it works that way. Newton wrote, "I frame no hypotheses." He did not want to guess. He did not want to speculate. He wanted only to describe facts. He wanted to give us a mathematical model that works, and he gave it to us. But he knew that this was not the final truth. He knew that behind his theory lay something deeper, something that we do not yet understand.
And he was right. Because 200 years later, a man appeared who showed that Newtonian physics is only an approximation that works in most cases, but that fails at the boundaries of knowledge. This man showed that time is not absolute, that space is not absolute, that gravity is not a force, but a curvature of space-time. That man's name was Albert Einstein. But before we turn to Einstein, let us talk about how Newtonian physics worked, because this is important. It is important to understand how successful it was. It is important to understand why it seemed like the final truth. And it is important to understand why it ultimately failed. Newtonian physics was based on the idea of absolute time and absolute space. Newton believed that time flows uniformly, regardless of what happens. He believed that space is a fixed stage on which events unfold. He believed that there is an absolute frame of reference, relative to which motion can be measured. He believed that the laws of physics are the same for all observers, regardless of their motion. This idea was intuitively understandable. It matched our everyday experience. We feel that time flows the same for everyone. We feel that space is the same for everyone. We feel that the laws of physics are the same for everyone. This seems obvious, but it is not. In reality, time is not absolute. Space is not absolute. The laws of physics are not the same for all observers. They are the same only for those who move at constant speed. For those who accelerate, the laws of physics change. This discovery belongs to Einstein, and it changed everything. But before we turn to Einstein, let us talk about how Newtonian physics was used to understand the world, because this is important. It is important to understand how successful it was. It is important to understand why it seemed like the final truth, and it is important to understand why it ultimately failed.
Newtonian physics allowed us to understand the motion of the planets. It allowed us to predict eclipses. It allowed us to calculate the trajectories of comets. It allowed us to understand the tides. It allowed us to understand the shape of the Earth. It allowed us to build bridges, ships, buildings. It allowed us to create the Industrial Revolution. It allowed us to change the world. But Newtonian physics had its limitations. It worked only for objects moving at low speeds. It worked only for objects in weak gravitational fields. It did not work for objects moving at speeds close to the speed of light. It did not work for objects in strong gravitational fields. It did not work for atoms and molecules. These limitations became apparent at the end of the 19th century. Scientists began to notice that Newtonian physics could not explain certain phenomena. For example, the orbit of Mercury. Mercury is the planet closest to the Sun. Its orbit differs slightly from the predictions of Newtonian physics. The difference was very small, only 43 arcseconds per century, but it was real, and it could not be explained within the framework of Newtonian physics. Scientists tried to find an explanation. They assumed that there was another planet that was affecting Mercury's orbit. They called this hypothetical planet Vulcan. They searched for it, but could not find it. They assumed that there was some other force affecting Mercury's orbit, but they could not find this force. This was a crack in Newtonian physics, a small, almost invisible crack. But it was real, and it waited for someone who could explain it. Another problem was light. Newton believed that light consisted of particles. He called them corpuscles. But at the beginning of the 19th century, Thomas Young showed that light behaves as a wave.
He conducted an experiment with two slits and showed that light creates an interference pattern, which is characteristic of waves. This was convincing evidence that light is a wave, but it created a new problem. If light is a wave, what does it travel through? A wave needs a medium to travel through. For sound, it is air. For water, it is water. For light, what? Scientists assumed that there is some medium that fills all of space. They called it the ether. They believed that light travels through the ether, the way sound travels through air. But the ether was elusive. Scientists tried to detect it. They conducted experiments to measure the speed of light in different directions. They assumed that the Earth moves through the ether, and therefore the speed of light should depend on direction. But they could not detect any difference. The speed of light was always the same, regardless of direction. This was a mystery. In 1887, American scientists Albert Michelson and Edward Morley conducted one of the most precise experiments in the history of science. They wanted to measure the speed of light in different directions. They used an interferometer, an instrument that allowed them to measure very small differences in the speed of light. They expected that the speed of light would be different in different directions, depending on the Earth's motion through the ether. But they found no difference. The speed of light was the same in every direction. This was one of the most important experiments in the history of science. It showed that the ether does not exist. It showed that the speed of light is constant. It showed that Newtonian physics could not explain this phenomenon. This was another crack in Newtonian physics, a crack that demanded an explanation. And the explanation came from a man who worked in a patent office in Bern. His name was Albert Einstein. He was a young man who had not been able to find a job at a university. He was modest, quiet, unnoticeable, but he was a genius. He asked questions that no one else asked. He sought answers that no one else sought. He found a solution that changed the world. In 1905, Einstein published an article called "On the Electrodynamics of Moving Bodies." In this article, he formulated the special theory of relativity. It was a theory that explained why the speed of light is constant. It was a theory that showed that time and space are not absolute. It was a theory that overturned our understanding of the universe. Einstein began with two postulates. First, the laws of physics are the same for all observers moving at constant speed. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion. These two postulates seemed simple, but their consequences were staggering. From these postulates, it followed that time is not absolute.
Time flows differently for different observers, depending on their speed. The faster an observer moves, the more slowly time flows for them. This phenomenon is called time dilation. It has been confirmed experimentally. Clocks on satellites run slower than clocks on Earth. This is accounted for in the GPS system. From these postulates, it followed that space is not absolute. The length of objects contracts in the direction of their motion. The faster an object moves, the shorter it becomes. This phenomenon is called length contraction. It has been confirmed experimentally. From these postulates, it followed that mass depends on speed. The faster an object moves, the greater its mass. This phenomenon is called relativistic mass increase. It has been confirmed experimentally. From these postulates, it followed that energy and mass are equivalent. E equals mc squared. This is the most famous formula in physics. It shows that mass can be converted into energy and energy into mass. This explains how nuclear reactors and atomic bombs work. The special theory of relativity was revolutionary. It showed that Newtonian physics is only an approximation that works for low speeds, but for speeds close to the speed of light, it no longer works. It needs to be replaced. But the special theory of relativity was incomplete. It explained motion at constant speed, but it did not explain acceleration. It did not explain gravity. It did not explain why planets move in orbits. It did not explain why an apple falls to the ground. It left these questions unanswered. Einstein knew this. He knew that his theory was incomplete. He knew that he had to find a way to include gravity in his theory. He knew that this would be his greatest achievement, and he began to work on it. It was a long and difficult task. Einstein spent 10 years creating the general theory of relativity. He worked on it intermittently. He searched for the mathematical apparatus that would allow him to describe gravity. He found it in Riemannian geometry. He used tensor calculus. He created a theory that was complex and elegant. In 1915, Einstein published the general theory of relativity. It was a theory that explained gravity as the curvature of space-time. He showed that mass curves space-time, and other objects move through curved space-time. This was a radical rethinking of gravity. It was not a force, but geometry. It was not attraction, but following a curve. The general theory of relativity explained what Newtonian physics could not. It explained the orbit of Mercury. It predicted the deflection of light in a gravitational field. It predicted the existence of black holes. It predicted the existence of gravitational waves. All of these predictions were confirmed experimentally. The general theory of relativity was a triumph. It was a theory that changed our understanding of the universe. It showed that space and time are not a fixed stage. They are a dynamic fabric that curves under the influence of mass. It showed that gravity is not a force, but a curvature of space-time. It showed that the universe is much more complex than we thought. But the general theory of relativity was not the final truth. It did not explain quantum phenomena. It did not explain how gravity works at the microscopic level. It did not explain what dark matter and dark energy are. It left these questions unanswered. And these questions await their answers. They await a new Einstein, a new genius who will ask new questions and find new answers. They await a new revolution in physics, a revolution that will change our understanding of the universe once again. But that will be in the next chapter. For now, let us pause on what we have learned. We learned that Aristotle created a theory of motion that was intuitively understandable, but mistaken. We learned that Galileo showed that motion does not require a constant force, and that all objects fall with the same acceleration. We learned that Newton created a universal theory of motion and gravity that worked for nearly 300 years. We learned that Einstein showed that time and space are not absolute, and that gravity is a curvature of space-time. We have come a long way. From Aristotle to Einstein, from the idea of natural places to the idea of curved space-time, from faith in authorities to trust in experiment, from simple observations to complex mathematical theories. And ahead of us lies an even longer road, because we do not yet know the final truth. We do not yet know how to unite the general theory of relativity and quantum mechanics. We do not yet know what dark matter and dark energy are. We do not yet know how the universe is structured at the deepest level. But we know that we are on the right path. We know that we can understand the world. We know that we can ask questions and find answers. We know that we can continue to seek the truth. And that is the most important thing. In the next chapter, we will see how quantum mechanics changed our understanding of motion. We will see how it showed that at the microscopic level, the world is structured very differently from what we thought. We will see how it showed that motion is not simply a change of position in space, but something much more complex and mysterious. But that will be in the next chapter. For now, let us simply rest and think about how far we have come. From Aristotle to Newton. From Newton to Einstein. From Einstein to quantum mechanics. We have come a long way, and ahead of us lies an even longer road. A road that will lead us to understand that the universe is much more complex than we thought. A road that will lead us to understand that motion is not simply a change of position in space, but something much more fundamental.
A road that will lead us to understand that we ourselves are part of this motion, that we ourselves are part of the universe, and that we ourselves are part of the great dance that continues forever. Einstein created the special theory of relativity in 1905. He was only 26 years old. He was working in a patent office in Bern, examining other people's inventions. He was not a professor. He was not a famous scientist. He was a modest clerk who did physics in his spare time. And he started a revolution. The special theory of relativity was simple and elegant. It was based on two postulates. First, the laws of physics are the same for all observers moving at constant speed. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion. These two postulates seemed harmless, but their consequences were staggering. From them, it followed that time is not absolute. Time flows differently for different observers, depending on their speed. The faster an observer moves, the more slowly time flows for them. This phenomenon is called time dilation. From them, it followed that space is not absolute. The length of objects contracts in the direction of their motion. The faster an object moves, the shorter it becomes. This phenomenon is called length contraction. From them, it followed that mass depends on speed. The faster an object moves, the greater its mass. This phenomenon is called relativistic mass increase. From them, it followed that energy and mass are equivalent, E equals mc squared. This is the most famous formula in physics. The special theory of relativity was revolutionary. It showed that Newtonian physics is only an approximation that works for low speeds. But for speeds close to the speed of light, it no longer works. It needs to be replaced. But the special theory of relativity was incomplete. It explained motion at constant speed, but it did not explain acceleration.
It did not explain gravity. It did not explain why planets move in orbits. It did not explain why an apple falls to the ground. It left these questions unanswered. Einstein knew this. He knew that his theory was incomplete. He knew that he had to find a way to include gravity in his theory. He knew that this would be his greatest achievement, and he began to work on it. But before we turn to the general theory of relativity, let us talk about what gravity is, because this is important. It is important to understand what Newton did, and it is important to understand what Einstein did. Newton said that gravity is a force that acts between any two bodies. He said that this force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. He said that this force acts instantly across any distance. This was a simple and elegant theory. It worked. But it did not explain how gravity acts across a distance.
It did not explain why gravity exists. It did not explain what gravity is. Einstein said that gravity is not a force. It is a curvature of space-time. He said that mass curves space-time,
and other objects move through curved space-time. This was a radical idea. It explained how gravity acts across a distance. It explained why gravity exists. It explained what gravity is. But to understand this idea, you need to understand what space-time is. Space-time is a four-dimensional structure that unites space and time. In Newtonian physics, space and time were separate. They were independent. In relativity, they are united. They are different aspects of the same structure. Imagine a rubber sheet. Now imagine placing a heavy ball on this sheet. The sheet sags. It curves. Now imagine placing a small marble on this sheet. The marble will roll along the curved surface. It will move along a curve. It will not move in a straight line because the surface is curved. This is an analogy for gravity.
Mass curves space-time, and other objects move through curved space-time. This analogy is imperfect, but it gives a sense of how gravity works. It shows that gravity is not a force, but geometry. It shows that moving through curved space-time is not the result of a force acting, but the result of following a curve. Einstein worked on this idea for 10 years. He searched for the mathematical apparatus that would allow him to describe the curvature of space-time. He found it in Riemannian geometry. He used tensor calculus. He created a theory that was complex and elegant. In 1915, Einstein published the general theory of relativity. It was a theory that explained gravity as the curvature of space-time. It was revolutionary. It changed our understanding of the universe. The general theory of relativity explained what Newtonian physics could not. It explained the orbit of Mercury. Mercury is the planet closest to the Sun. Its orbit differs slightly from the predictions of Newtonian physics. The difference was very small, only 43 arc-seconds per century, but it was real, and it could not be explained within the framework of Newtonian physics. The general theory of relativity explained this difference. It showed that it arises from the curvature of space-time around the Sun. The general theory of relativity predicted the deflection of light in a gravitational field. Light passing near a massive object should be deflected. This prediction was confirmed during a solar eclipse in 1919. The British astronomer Arthur Eddington measured the positions of stars during the eclipse. He found that they had shifted. The shift matched the predictions of the general theory of relativity. It was a triumph. Einstein became famous. He became the most famous scientist in the world. The general theory of relativity predicted the existence of black holes. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from it. This prediction was made by Carl Schwarzschild in 1916. He found a solution to Einstein's equations for a spherically symmetric, massive object. He showed that if an object is sufficiently compressed, it creates a region from which nothing can escape. This was a black hole. The general theory of relativity predicted the existence of gravitational waves. Gravitational waves are ripples in space-time that travel at the speed of light. They are created by the motion of massive objects. This prediction was confirmed in 2015. The LIGO detectors registered gravitational waves from the merger of two black holes. It was a triumph. It was confirmation of the general theory of relativity. The general theory of relativity was a triumph. It was a theory that changed our understanding of the universe. It showed that space and time are not a fixed stage. They are a dynamic fabric that curves under the influence of mass. It showed that gravity is not a force, but a curvature of space-time. It showed that the universe is much more complex than we thought. But the general theory of relativity was incomplete. It did not explain quantum phenomena.
It did not explain how gravity works at the microscopic level. It did not explain what dark matter and dark energy are. It left these questions unanswered, and these questions await their answers. They await a new Einstein, a new genius who will ask new questions and find new answers. They await a new revolution in physics, a revolution that will change our understanding of the universe once again. But before we turn to quantum mechanics, let us talk about what quantum mechanics is, because this is important. It is important to understand what it did, and it is important to understand what it did not do.
Quantum mechanics is a theory that describes the behavior of matter and energy at the microscopic level. It was created at the beginning of the 20th century. It was created by a group of scientists who were working on problems that classical physics could not solve. They worked on the problem of black body radiation. They worked on the problem of the photoelectric effect. They worked on the problem of atomic spectra. They created a theory that was strange and contradictory, but it worked. Quantum mechanics showed that, at the microscopic level, the world is structured very differently from what we thought. It showed that energy is not continuous, it is discrete. It showed that light is both a wave and a particle. It showed that electrons are both waves and particles. It showed that the position and speed of a particle cannot be known simultaneously. It showed that observation affects the outcome. It showed that the world is much more complex than we thought. Quantum mechanics was revolutionary. It changed our understanding of reality. But it did not explain gravity. It did not explain how gravity works at the microscopic level. It left this question unanswered. And this question awaits its answer. It awaits a new revolution in physics, a revolution that will unite the general theory of relativity and quantum mechanics, a revolution that will create a theory of quantum gravity, a revolution that will change our understanding of the universe once again. But that will be in the next chapter. For now, let us pause on what we have learned. We learned that Aristotle created a theory of motion that was intuitively understandable, but mistaken. We learned that Galileo showed that motion does not require a constant force and that all objects fall with the same acceleration. We learned that Newton created a universal theory of motion and gravity that worked for nearly 300 years. We learned that Einstein showed that time and space are not absolute, and that gravity is a curvature of space-time. We learned that quantum mechanics showed that at the microscopic level, the world is structured very differently from what we thought. We have come a long way. From Aristotle to quantum mechanics, from the idea of natural places to the idea of the probabilistic nature of reality, from faith in authorities to trust in experiment, from simple observations to complex mathematical theories. And ahead of us lies an even longer road. Because we do not yet know the final truth. We do not yet know how to unite the general theory of relativity and quantum mechanics. We do not yet know what dark matter and dark energy are. We do not yet know how the universe is structured at the deepest level. But we know that we are on the right path. We know that we can understand the world. We know that we can ask questions and find answers. We know that we can continue to seek the truth. And that is the most important thing. In the next chapter, we will see how quantum mechanics changed our understanding of motion. We will see how it showed that at the microscopic level, the world is structured very differently from what we thought. We will see how it showed that motion is not simply a change of position in space, but something much more complex and mysterious. But that will be in the next chapter. For now, let us simply rest and think about how far we have come. From Aristotle to Newton, from Newton to Einstein, from Einstein to quantum mechanics. We have come a long way, and ahead of us lies an even longer road, a road that will lead us to understand that the universe is much more complex than we thought, a road that will lead us to understand that motion is not simply a change of position in space,
but something much more fundamental. A road that will lead us to understand that we ourselves are part of this motion, that we ourselves are part of the universe.
And that we ourselves are part of the great dance that continues forever. Einstein showed that space and time are not absolute. They are part of a single structure, space-time. And this structure curves under the influence of mass. This changed our understanding of motion. Motion is not simply movement through space. It is movement through curved space-time. But that is not all. Quantum mechanics showed that at the microscopic level, the world is structured very differently from what we thought. It showed that motion at the microscopic level is not simply movement through space. It is something much more complex and mysterious. It is a dance of probabilities, a dance in which particles can be in several places at once, a dance in which observation affects the outcome, a dance in which the world is structured very differently from what we thought. And this dance continues. It continues inside every atom. It continues inside every molecule. It continues inside every living being.
It continues inside each of us. We are part of this dance. We are part of this motion. We are part of the universe. And we continue to explore this dance. We continue to ask questions. We continue to seek answers. We continue to move forward. Because this is the essence of science, the essence of knowledge, the essence of the human spirit. We do not stop. We do not give up. We continue to move forward. Because we know that ahead of us lie new discoveries, new revolutions, new changes in our understanding of the universe. And this is beautiful. This is beautiful because it means that we will never stop learning. We will never stop growing. We will never stop developing. We will continue to explore the universe. We will continue to seek the truth. We will continue to move forward. Because this is our destiny. Our destiny is to understand the world. Our destiny is to comprehend the universe. Our destiny is to be part of the great dance that continues forever. Einstein completed the general theory of relativity in 1915. It was his greatest achievement. It was a theory that changed our understanding of the universe. But he did not stop there. He continued to work. He continued to think. He continued to ask questions. And one of the questions he asked was about how the universe is structured as a whole. In 1917, Einstein applied his new theory to the cosmos. He wanted to understand how the universe is structured. He wanted to understand whether it is static or dynamic. He wanted to understand whether it is expanding or contracting. And he discovered something astonishing. His equations showed that the universe cannot be static. It must either expand or contract. It cannot remain unchanged. This was a shocking discovery. At that time, everyone believed that the universe was static. Everyone believed that it existed forever in an unchanging state. Everyone believed that it did not change.
But Einstein's equations said otherwise. They said that the universe must change. They said that it must either expand or contract. Einstein was dismayed. He did not want to believe his own equations. He believed that the universe must be static. He believed that it must be eternal and unchanging. He believed that his theory should predict a static universe, but it did not. It predicted a dynamic universe. To save his theory, Einstein added a new term to his equations. He called it the cosmological constant. This term was needed to balance gravity and create a static universe. It was an artificial solution. It was a solution that did not follow from the theory. It was a solution that was added so that the theory would match Einstein's prejudices. Einstein later called this his greatest mistake, because a few years later, it was discovered that the universe is indeed expanding. It is not static. It is dynamic. It is changing. And the cosmological constant was not needed.
It was a mistake. But that is not all.
Einstein did not know that his theory predicted not only the expansion of the universe, it also predicted the existence of black holes. It also predicted the existence of gravitational waves. It also predicted the existence of gravitational time dilation. All of these predictions were made within a few years of the publication of the general theory of relativity. Black holes were predicted by Carl Schwarzschild in 1916. Schwarzschild was a German physicist who was serving in the army during the First World War. He found a solution to Einstein's equations for a spherically symmetric massive object. He showed that if an object is sufficiently compressed, it creates a region from which nothing can escape. This was a black hole. Schwarzschild sent his work to Einstein. Einstein was impressed. He presented Schwarzschild's work to the Prussian Academy of Sciences, but he was not sure that black holes really exist. He thought it was a mathematical curiosity. He thought that nature would not allow objects to be compressed to such a degree. He was wrong. Black holes exist. They have been discovered. They are real objects in the universe. Gravitational waves were predicted by Einstein in 1916. He showed that his equations allow wave solutions. He showed that gravitational waves are ripples in spacetime that travel at the speed of light. He showed that they are created by the motion of massive objects, but he was not sure that they could be detected. He thought they were too weak. He was wrong. Gravitational waves were detected in 2015. The LIGO detectors registered gravitational waves from the merger of two black holes. It was a triumph. It was confirmation of the general theory of relativity. Gravitational time dilation was predicted by Einstein in 1911. He showed that time flows more slowly in strong gravitational fields. This prediction was confirmed in 1960. The physicists Robert Pound and Glenn Rebka measured gravitational time dilation in a laboratory. They showed that time flows more slowly on the lower floor of a building than on the upper floor. This was confirmation of the general theory of relativity. The general theory of relativity was a triumph. It was a theory that changed our understanding of the universe. It showed that space and time are not a fixed stage. They are a dynamic fabric that curves under the influence of mass. It showed that gravity is not a force, but a curvature of space-time. It showed that the universe is much more complex than we thought. But the general theory of relativity was incomplete. It did not explain quantum phenomena. It did not explain how gravity works at the microscopic level. It did not explain what dark matter and dark energy are. It left these questions unanswered. And these questions await their answers. They await a new Einstein. A new genius who will ask new questions and find new answers. They await a new revolution in physics, a revolution that will change our understanding of the universe once again. But before we turn to quantum mechanics, let us talk about what quantum mechanics is, because this is important. It is important to understand what it did, and it is important to understand what it did not do. Quantum mechanics is a theory that describes the behavior of matter and energy at the microscopic level. It was created at the beginning of the 20th century. It was created by a group of scientists who were working on problems that classical physics could not solve. They worked on the problem of black body radiation. They worked on the problem of the photoelectric effect. They worked on the problem of atomic spectra. They created a theory that was strange and contradictory, but it worked. Quantum mechanics showed that at the microscopic level, the world is structured very differently from what we thought. It showed that energy is not continuous, it is discrete. It showed that light is both a wave and a particle. It showed that electrons are both waves and particles. It showed that the position and speed of a particle cannot be known simultaneously. It showed that observation affects the outcome. It showed that the world is much more complex than we thought. Quantum mechanics was revolutionary. It changed our understanding of reality. But it did not explain gravity. It did not explain how gravity works at the microscopic level.
it left this question unanswered. And this question awaits its answer. It awaits a new revolution in physics. A revolution that will unite the general theory of relativity and quantum mechanics. A revolution that will create a theory of quantum gravity. A revolution that will change our understanding of the universe once again.
But that will be in the next chapter. For now, let us pause on what we have learned. We learned that Aristotle created a theory of motion that was intuitively understandable, but mistaken. We learned that Galileo showed that motion does not require a constant force, and that all objects fall with the same acceleration. We learned that Newton created a universal theory of motion and gravity that worked for nearly 300 years. We learned that Einstein showed that time and space are not absolute, and that gravity is a curvature of space-time. We learned that the general theory of relativity predicted black holes, gravitational waves, and gravitational time dilation. We learned that all of these predictions were confirmed experimentally. We have come a long way, from Aristotle to Einstein, from the idea of natural places to the idea of curved space-time, from faith in authorities to trust in experiment, from simple observations to complex mathematical theories.
And ahead of us lies an even longer road, because we do not yet know the final truth. We do not yet know how to unite the general theory of relativity and quantum mechanics. We do not yet know what dark matter and dark energy are. We do not yet know how the universe is structured at the deepest level. But we know that we are on the right path. We know that we can understand the world. We know that we can ask questions and find answers. We know that we can continue to seek the truth. And that is the most important thing. In the next chapter, we will see how quantum mechanics changed our understanding of motion. We will see how it showed that at the microscopic level, the world is structured very differently from what we thought. We will see how it showed that motion is not simply a change of position in space, but something much more complex and mysterious. But that will be in the next chapter. For now, let us simply rest and think about how far we have come. From Aristotle to Newton, from Newton to Einstein, from Einstein to quantum mechanics, we have come a long way, and ahead of us lies an even longer road, a road that will lead us to understand that the universe is much more complex than we thought, a road that will lead us to understand that motion is not simply a change of position in space, but something much more fundamental. A road that will lead us to understand that we ourselves are part of this motion, that we ourselves are part of the universe, and that we ourselves are part of the great dance that continues forever. Einstein showed that space and time are not absolute. They are part of a single structure, space-time, and this structure curves under the influence of mass. This changed our understanding of motion. Motion is not simply movement through space. It is movement through curved space-time. But that is not all. Quantum mechanics showed that at the microscopic level, the world is structured very differently from what we thought.
It showed that motion at the microscopic level is not simply movement through space. It is something much more complex and mysterious. It is a dance of probabilities. A dance in which particles can be in several places at once. A dance in which observation affects the outcome. A dance in which the world is structured very differently from what we thought. And this dance continues. It continues inside every atom. It continues inside every molecule. It continues inside every living being. It continues inside each of us. We are part of this dance. We are part of this motion. We are part of the universe. And we continue to explore this dance. We continue to ask questions. We continue to seek answers. We continue to move forward. Because this is the essence of science, the essence of knowledge, the essence of the human spirit. We do not stop. We do not give up.
we continue to move forward because we know that ahead of us lie new discoveries, new revolutions,
new changes in our understanding of the universe. And this is beautiful. This is beautiful because it means that we will never stop learning. We will never stop growing. We will never stop developing. We will continue to explore the universe. We will continue to seek the truth. We will continue to move forward because this is our destiny. Our destiny is to understand the world. Our destiny is to comprehend the universe. Our destiny is to be part of the great dance that continues forever. The general theory of relativity and quantum mechanics are the two greatest theories in the history of physics. They both work. They are both confirmed experimentally. But they are incompatible. They cannot both be true at the same time. They contradict each other. This is the biggest problem in modern physics. This is a problem that awaits its solution. And the solution to this problem will be the next great breakthrough. It will change our understanding of the universe. It will show us how the world is structured at the deepest level. It will unite gravity and quantum mechanics. It will create a theory of everything. And this will be the greatest achievement in the history of science. But we are still far from that. We do not yet know how to do it. We do not yet know which theory will be correct. We do not yet know when it will happen. But we know that it will happen. Because science does not stand still. It moves forward, it develops, it grows, and it never stops. And we will continue to move forward. We will continue to ask questions. We will continue to seek answers. We will continue to explore the universe. Because this is our destiny. Our destiny is to understand the world. Our destiny is to comprehend the universe. Our destiny is to be part of the great dance that continues forever. The 20th century gave physics its two greatest theories. The general theory of relativity, which explained gravity as the curvature of space-time, and quantum mechanics, which explained the behavior of matter and energy at the microscopic level. Both theories were revolutionary. Both theories changed our understanding of the universe. Both theories were confirmed experimentally, but they were incompatible. They could not both be true at the same time. They contradicted each other. This was the biggest problem in physics, a problem that awaited its solution, a problem that tormented the greatest minds of the 20th century, and it continues to torment them to this day. But before we turn to this problem, let us talk about quantum mechanics, because this is important. It is important to understand what it did, and it is important to understand what it did not do. Quantum mechanics was born at the beginning of the 20th century. It was born from attempts to solve problems that classical physics could not solve. The first such problem was black body radiation. A black body is an ideal object that absorbs all radiation falling on it. When a black body is heated, it radiates energy. Classical physics could not explain exactly how it radiates. It predicted that a black body would radiate an infinite amount of energy at high frequencies. This was absurd. It was called the ultraviolet catastrophe. In 1900, Max Planck solved this problem. He assumed that energy is not emitted continuously, but in discrete portions. He called these portions quanta. He showed that the energy of a quantum is proportional to the frequency of the radiation. This was a revolutionary assumption. It contradicted classical physics, but it worked. It explained black body radiation. In 1905, Einstein used the idea of quanta to explain the photoelectric effect. The photoelectric effect is a phenomenon in which light knocks electrons out of metal. Classical physics could not explain why the energy of the ejected electrons depends on the frequency of the light rather than its intensity. Einstein assumed that light consists of particles, photons. The energy of a photon is proportional to the frequency of the light.
This explained the photoelectric effect. It was confirmation of quantum theory. In 1913, Niels Bohr used quantum theory to explain the structure of the atom. He assumed that electrons in an atom can only exist in certain orbits. He assumed that electrons can jump from one orbit to another, emitting or absorbing quanta of energy. This explained atomic spectra. It was confirmation of quantum theory. In the 1920s, quantum mechanics was fully formulated. This was done by a group of scientists: Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Max Born, Niels Bohr. They created a theory that was strange and contradictory, but it worked. It explained the behavior of atoms and molecules.
It explained chemical bonds. It explained the properties of materials. It explained everything that happens at the microscopic level. Quantum mechanics showed that at the microscopic level, the world is structured very differently from what we thought. It showed that energy is not continuous. It is discrete. It showed that light is both a wave and a particle. It showed that electrons are both waves and particles. It showed that the position and speed of a particle cannot be known simultaneously. It showed that observation affects the outcome. It showed that the world is much more complex than we thought. Heisenberg's uncertainty principle was one of the most important discoveries of quantum mechanics. It states that it is impossible to simultaneously measure the exact position and momentum of a particle. The more precisely we measure the position, the less precisely we know the momentum, and vice versa. This is not just a limitation of measuring instruments.
This is a fundamental property of nature. This means that at the microscopic level, the world is not deterministic. It is probabilistic. We cannot predict where a particle will end up. We can only calculate the probability that it will end up in one place or another. This was a shocking discovery. It contradicted everything we knew about the world. It contradicted the idea of determinism. It contradicted the idea that the world is governed by laws that can be predicted with absolute certainty. It showed that at the deepest level, the world is unpredictable. It is random. It is probabilistic. Einstein could not accept this. He said, "God does not play dice." He believed that quantum mechanics was incomplete. He believed that there must be hidden variables that determine the behavior of particles. He believed that we simply do not know these variables. He believed that when we discover them, we will be able to predict the behavior of particles with absolute certainty. But he was wrong. Experiments showed that there are no hidden variables. The world really is probabilistic. The world really is random. The world really is unpredictable. This was confirmed in the 1960s. John Bell formulated a theorem that made it possible to test whether hidden variables exist. Experiments showed that they do not. Quantum mechanics was correct. The world really is probabilistic. But quantum mechanics did not explain gravity. It did not explain how gravity works at the microscopic level. It left this question unanswered. And this question awaits its answer. It awaits a new revolution in physics. A revolution that will unite the general theory of relativity and quantum mechanics. A revolution that will create a theory of quantum gravity. A revolution that will change our understanding of the universe once again. There are several attempts to create such a theory. The most famous of them is string theory.
String theory assumes that the fundamental objects in the universe are not particles, but one-dimensional strings. These strings can vibrate at different frequencies. Different vibration frequencies correspond to different particles. String theory unites gravity and quantum mechanics. It is a candidate for a theory of everything, but it has a problem. It requires the existence of additional dimensions. It requires the existence of 10 or 11 dimensions. We do not observe these dimensions. They must be curled up. They must be too small for us to notice. This is difficult to test experimentally. Another attempt is loop quantum gravity. Loop quantum gravity does not assume the existence of additional dimensions. It tries to quantize space-time itself. It assumes that space-time consists of discrete pieces. It assumes that there is a minimum length. This is a complex and elegant theory, but it too has a problem. It does not make specific predictions that can be tested experimentally. None of these theories is final. None of them has been confirmed experimentally. None of them is universally accepted. The problem of quantum gravity remains unsolved. But this does not mean that we have not made progress. We have made great progress. We have understood how the universe is structured at the macroscopic level. We have understood how the universe is structured at the microscopic level. We have understood that these two descriptions are incompatible. We have understood that a new theory is needed. We are searching for this theory. We are working on this theory. We are getting closer to this theory. And we know that this theory will be found. Because science does not stand still. It moves forward, it develops, it grows, and it never stops. But let us return to where we began. We began with motion. We began with the question, what is motion? We began with the fact that motion is a fundamental property of the universe. We began with the fact that the universe is never at rest. It is always moving. It is always changing. It is always developing. We have come a long way. We began with Aristotle. We saw how he created a theory of motion that was intuitively understandable, but mistaken. We saw how Galileo showed that motion does not require a constant force. We saw how Newton created a universal theory of motion and gravity. We saw how Einstein showed that time and space are not absolute. We saw how quantum mechanics showed that at the microscopic level, the world is structured very differently from what we thought. We learned that motion is not simply a change of position in space. It is something much more fundamental. It is something that permeates the entire universe. It is something that determines the very structure of reality. We learned that the universe is not a static stage. It is a dynamic fabric. A fabric that is constantly moving. A fabric that is constantly changing.
A fabric that is constantly developing. We learned that we ourselves are part of this motion. We ourselves are part of this fabric. We ourselves are part of the universe. And this is beautiful. This is beautiful because it means that we are not separate from the universe. We are not outside observers. We are participants. We are part of the great dance that continues forever. We dance this dance. We move together with the universe. We change together with the universe. We develop together with the universe. And we never stop. Because stopping is an illusion. Rest is an illusion. The only reality is motion. And this knowledge liberates. It liberates us from the illusion of stillness. It liberates us from the illusion of permanence. It liberates us from the illusion of control. We cannot control the universe. We cannot stop the motion. We cannot freeze in time. We can only move together with it. We can only be part of this great dance. And this is beautiful.
This is beautiful because it means that we are free. We are free to move. We are free to change. We are free to develop. We are free to be part of the universe. We are motion. We are change. We are development. We are the universe. And we continue to move. We continue to change. We continue to develop. We continue to be part of the universe. And we never stop. Because stopping is an illusion. Rest is an illusion. The only reality is motion. And we are motion. We are the universe. We are the dance, and we continue to dance, infinitely, eternally, without stopping. So when you lie here now and feel motionless, remember, this is an illusion. You were never motionless. You will never be motionless. You are always moving. You are always part of the universe. You are always part of the great dance. And this dance continues. It continues inside you. It continues around you. It continues everywhere. It continues always. And this is the most beautiful thing to know.
That we are not separate from the universe. That we are not alone. That we are part of something greater. That we are part of a motion that never ends. That we are part of a dance that continues forever. And we can enjoy this dance. We can enjoy this motion. We can enjoy this life. Because this is life. This is the universe. This is us. And this is the most beautiful thing to know. That we exist. That we move. That we dance. That we are part of everything. That we are part of infinite motion. That we are part of the infinite dance. And that this dance never ends. It continues. Always. Infinitely. Eternally.
The 20th century gave physics two great gifts. The general theory of relativity, which showed us that gravity is the curvature of space-time, and quantum mechanics, which showed us that at the smallest scales, the universe is not a machine, but a dance. Two theories, two visions of reality, both brilliant, both confirmed by experiment, and utterly incompatible. This is where we find ourselves now, standing at the edge of knowledge, looking out at a universe that seems to be made of two different substances, playing by two different sets of rules. On one side, the large. Planets, stars, galaxies. The realm of Einstein, where space-time is smooth and continuous, where gravity bends light and slows time. On the other side, the small. Atoms, electrons, photons. The realm of quantum mechanics, where particles are waves, where energy comes in discrete packets, where the act of looking changes what you find. The problem is not that one theory is wrong. Both are right. Both have been tested to extraordinary precision. The problem is that they cannot both be true at the same time in the same place. They contradict each other at the deepest level. And this contradiction has been the central problem of physics for nearly a century. But before we grapple with this problem, we need to understand quantum mechanics more deeply. We have touched on it, but we have not truly felt its strangeness. We need to sit with its ideas, to let them sink in. Because quantum mechanics is not just a set of equations, it is a new way of understanding reality itself. And once you understand it, you can never see the world the same way again. Let us start where we left off. The quantum revolution began with Max Planck in 1900, when he discovered that energy comes in discrete packets, which he called quanta. It was a desperate solution to a problem that had baffled physicists for decades, the problem of black body radiation. When you heat an object, it glows. First red, then orange, then yellow, then white. Classical physics could not explain why the glow did not continue into the ultraviolet, why the energy did not increase without limit. Planck found that if he assumed energy could only be emitted in discrete chunks, the math worked perfectly. It was a fix, a patch. He did not believe it was real. He thought it was a mathematical trick. But Einstein took it seriously. In 1905, he used Planck's idea to explain the photoelectric effect. Light shining on a metal surface knocks electrons loose. Classical physics said the energy of the electrons should depend on the brightness of the light.
but experiments showed that it depends on the color. Bright red light does nothing. Dim blue light knocks electrons free. Einstein realized that light itself must come in discrete packets, each carrying an amount of energy determined by its color. He called them light quanta. We now call them photons.
This was the first crack in the classical worldview. Light, which everyone had accepted as a wave for over a century, also behaves like a particle. It was the beginning of wave-particle duality, the idea that the universe at its smallest scales does not obey our everyday intuitions. Then came Bohr. In 1913, he applied the quantum idea to the atom. He proposed that electrons orbit the nucleus only in certain allowed orbits, like rungs on a ladder. They cannot exist between these orbits. When they jump from one orbit to another, they emit or absorb a single photon of exactly the right energy. This explained the spectral lines of hydrogen, the specific colors of light that hydrogen emits when heated. It was a triumph. But it was also strange. Why should electrons only occupy certain orbits? Bohr could not say. He simply postulated it. It was a rule without an explanation. The explanation came from Louis de Broglie, a French prince who had switched from history to physics. In 1924, he proposed that if waves can behave like particles, then particles should behave like waves. An electron, he said, has a wavelength, and the allowed orbits of the atom are simply the orbits where the electron's wave fits neatly around the nucleus, like a standing wave on a guitar string. If the wave does not fit, it cancels itself out. It cannot exist. This was beautiful. It explained Bohr's arbitrary rule. The quantization of orbits was not a mysterious decree. It was a consequence of the wave nature of the electron. And then the experiments confirmed it. In 1927, Clinton Davison and Lester Germer fired electrons at a nickel crystal and observed a diffraction pattern. The electrons behaved exactly like waves. The wave nature of matter was real. De Broglie won the Nobel Prize for this in 1929. But the double-slit experiment, which we have mentioned before, goes even further. It reveals something so strange that even physicists struggle to fully accept it. Here is the setup. You take a source of particles, say electrons or photons, and you fire them one at a time at a barrier with two slits. Behind the barrier is a screen that detects where each particle lands. If you fire enough particles, you see a pattern of alternating bright and dark bands. This is the interference pattern of waves. Each particle, somehow, is interfering with itself. It is going through both slits at once. Now here is the twist. If you place a detector at one of the slits to measure which slit the particle passes through, the interference pattern disappears. The particles behave like ordinary particles, going through one slit or the other. The act of measuring, of looking, destroys the wave-like behavior. The particle no longer takes both paths, it takes one. Think about what this means. The particle does not have a definite path until you observe it. It exists in a superposition of states, going through both slits simultaneously. But the moment you look, the superposition collapses. The wave function, as physicists call it, snaps to a single outcome. The act of observation does not reveal reality, it creates reality. This is not a philosophical interpretation. This is what the math says. This is what the experiments show. The universe at its smallest scales is not a collection of objects with definite properties. It is a collection of probabilities, possibilities, potentialities. And these possibilities only become actual when they are observed. Erwin Schrödinger, who gave us the wave equation that describes this behavior,
was so troubled by this that he invented a famous thought experiment. He imagined a cat sealed in a box with a vial of poison and a radioactive atom. If the atom decays, the poison is released and the cat dies. If it does not decay, the cat lives. According to quantum mechanics, until you open the box, the atom is in a superposition of decayed and not decayed, which means the cat is also in a superposition of alive and dead. It is both at the same time. Only when you open the box does the wave function collapse and one outcome becomes real. Schrödinger intended this as a criticism. He wanted to show how absurd quantum mechanics was if taken literally. But the absurdity is not in the math. The absurdity is in reality itself. At the quantum level, things really can be in multiple states at once. The cat is alive and dead. The electron is here and there. The photon is both a wave and a particle. The uncertainty principle of Werner Heisenberg adds another layer of strangeness. He showed that there are pairs of properties, like position and momentum, that cannot both be known with perfect precision. The more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. This is not a limitation of our instruments. It is a fundamental property of nature. The particle does not have both a definite position and a definite momentum at the same time. These properties do not exist until they are measured. Think about that for a moment. The universe, at its deepest level, is not determinate. It is not a machine ticking along according to predictable laws. It is a realm of possibility and probability. The future is not fixed. It is a range of outcomes, each with a certain likelihood. And the act of measurement, the act of observation, is what selects one outcome from the range of possibilities. This was too much for Einstein. He spent the last 30 years of his life arguing against it. He said, "God does not play dice." He believed that there must be something underneath quantum mechanics, some deeper reality that we have not yet discovered. He believed that the randomness and uncertainty were signs of our ignorance, not fundamental features of nature. But Einstein was wrong. The experiments have shown it again and again. In the 1960s, John Bell derived a mathematical inequality that could distinguish between quantum mechanics and any theory that assumed hidden variables, any theory that assumed particles had definite properties all along. The experiments violated Bell's inequality. The predictions of quantum mechanics were confirmed. The universe really is probabilistic. The randomness really is fundamental. And then came entanglement. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that attempted to show quantum mechanics was incomplete. They proposed a thought experiment in which two particles are created in such a way that their properties are linked or entangled. If you measure one particle, you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance. He argued that it was absurd.
There must be hidden variables that determine the states of the particles in advance. But experiments showed that entanglement is real. The particles do not have definite states until they are measured. And when one is measured, the other instantly becomes determined, even if they are on opposite sides of the universe. This is not a signal traveling faster than light. There is no information being transmitted. It is something stranger. The two particles are not two separate things. They are a single quantum state spread across space. Measuring one does not send a signal to the other. It simply reveals that the single state has a particular property. This is the heart of quantum mechanics. It is not a theory about objects. It is a theory about relationships. It is a theory about information. The universe at its deepest level is not made of stuff. It is made of connections. It is made of correlations. It is made of information that only exists when observed.
What does this mean for motion? We have been talking about motion as a change of position in space. But at the quantum level, position itself is not a fixed property. A particle does not have a definite position until you measure it. It is not that you do not know where it is. It is that there is no fact of the matter about where it is. The question, "Where is the electron?" does not have an answer until you look. Motion, then, is not a continuous path from one place to another. It is a series of discrete jumps, each one triggered by an observation. Between observations, the particle does not move. It exists as a cloud of probabilities spread out over space. This is not a poetic interpretation. This is what the mathematics describes. This is what the experiments confirm. And yet, we do not experience this strangeness in our everyday lives. We do not see cats that are both alive and dead. We do not see objects in two places at once. Why not? The answer is decoherence.
When a quantum system interacts with its environment, the delicate superpositions are lost. The wave function collapses. The system becomes classical. The reason the quantum world seems so strange is that we are macroscopic creatures, living in a macroscopic world, surrounded by noise and interactions that destroy quantum behavior. But the quantum world is still there. It is the foundation of everything. The atoms in your body, the molecules in the air, the light from the stars, all of it obeys quantum rules. The reason the ground is solid is quantum mechanics. The reason the sun shines is quantum mechanics. The reason your phone works is quantum mechanics. The strangeness is not somewhere else. It is everywhere. It is just hidden beneath the surface of our everyday experience. And what about the future? What about the strange, unresolved questions? Quantum mechanics is the most successful theory in the history of science.
It has been tested to more decimal places than any other theory.
But it is not complete. It does not explain gravity. It does not explain why there is something rather than nothing. It does not explain consciousness. But perhaps the most profound thing quantum mechanics has taught us is this. The universe is not a machine. It is not a clockwork mechanism ticking along according to deterministic laws. It is a dance of probabilities and possibilities. A dance in which the observer is not a passive spectator, but an active participant. A dance in which the act of looking changes the dance itself. You are not separate from the universe. You are part of it. And every time you look, every time you observe, you are not just discovering reality, you are helping to create it. This is not mysticism. This is physics. This is what the math tells us. This is what the experiments confirm. So when you lie here now, feeling the stillness of your body, remember, on the quantum level, your atoms are dancing. They are buzzing with energy and possibility. They are in constant motion, even when you are perfectly still. The electrons in your body do not have definite positions. They are spread out in clouds of probability. They are here and there and everywhere at once. And the only reason you experience yourself as solid and stable is that trillions of quantum interactions are happening every instant, creating the illusion of classical reality. We have come a long way. From the prison of common sense, where Aristotle told us that rest is natural and motion needs a cause. Through the great revolution of Galileo, who showed us that motion is the natural state. through the universal law of Newton, who united the earthly and the heavenly, through the crack in the absolute, where Einstein showed us that time and space are not fixed,
and now through the quantum dance, where we have learned that reality itself is not fixed until we look. The story is not over. It continues. In the next chapter, we will look at the biggest unanswered questions in physics. The contradiction between general relativity and quantum mechanics, the search for a theory of everything, the dark matter and dark energy that make up most of the universe, the possibility that our universe is just one of many. These are not signs of failure. They are invitations. They are the next part of the dance, waiting for us to join in. But for now, let us rest. Let the quantum dance continue inside you, in every atom, in every cell. The probabilities are still swirling. The possibilities are still open. The wave function of your existence is still spreading out, a cloud of potential, waiting to collapse into the next moment. And when it does, you will be part of that collapse. You will be part of the creation of reality.
You will be part of the great dance that continues forever. So, let that thought settle. You are not just watching the universe, you are part of the universe. You are not just moving through time, you are part of time. You are not just living in the world, you are part of the world. And the dance goes on, inside you and outside you, in every atom, in every star, in every corner of the cosmos. The quantum dance is the deepest truth we have ever found, and it is a dance of joy, a dance of possibility, a dance of connection. So, rest now. Let the dance continue without you. You will join it again in the morning. For now, just be, just breathe, just let the quantum waves wash over you, carrying you gently into the stillness of sleep. We have come a long way, from the ancient Greeks who looked at the stars and saw the will of the gods, from Aristotle, who built a world of natural places and purposes, a world where rest was natural and motion required a cause, through Galileo, who rolled balls down inclined planes and showed that motion is the natural state, through Newton, who united the earthly and the heavenly with a single law of gravity, through Einstein, who revealed that space and time are not a fixed stage, but a living fabric that curves and bends, through the quantum revolution, which showed us that at the smallest scales, reality is not a machine, but a dance of probabilities. And here we are, at the edge of knowledge, standing at the boundary between what we understand and what we do not. The two great theories of the 20th century, general relativity and quantum mechanics, are both brilliant. Both have been confirmed by countless experiments. Both describe their domains with extraordinary precision, but they cannot both be true. They contradict each other at the deepest level. This is the central problem of modern physics, the problem of quantum gravity, the problem of how to unite the large and the small, the problem of understanding the universe as a single, coherent whole. Let us understand why these two theories are incompatible. General relativity is a theory of geometry. It tells us that gravity is not a force, but the curvature of space-time. Mass and energy warp the fabric of space-time, and other objects move along the curves of that warped fabric. It is a beautiful, elegant theory. It describes the universe on the largest scales: planets, stars, galaxies, the expansion of the cosmos itself. Quantum mechanics is a theory of probabilities. It tells us that at the smallest scales, the universe is not deterministic. Particles do not have definite properties until they are measured. They exist in superpositions of states. They are described by wave functions that evolve according to the Schrödinger equation. It is a strange, counterintuitive theory, but it is the most successful theory in the history of science. It describes the behavior of atoms, molecules, particles, the entire microscopic world. The problem is that the two theories speak different languages. General relativity speaks the language of geometry and continuous fields. Quantum mechanics speaks the language of probability and discrete quanta. When you try to apply quantum mechanics to gravity, the math breaks down. You get infinities. Nonsense. The equations refuse to give meaningful answers. This is not a small problem. It is the central problem of theoretical physics, and it has been unsolved for nearly a century. Why is it so hard? The answer lies in the nature of gravity itself. Gravity is incredibly weak compared to the other forces of nature. The electromagnetic force, the force that holds atoms together, is about 10 to the 36th power times stronger than gravity. That is a 1 followed by 36 zeros. Gravity is so weak that we only notice it when we have enormous amounts of mass, like planets and stars. At the level of individual particles, gravity is essentially negligible. It is so weak that we can safely ignore it in most quantum calculations. But when you try to calculate quantum effects of gravity, the weakness becomes a problem. To detect the quantum nature of gravity, you would need to probe distances so small that they are beyond the reach of any current or foreseeable technology. The scale at which quantum gravity becomes important is called the Planck scale. It is about 10 to the minus 35 meters. That is, a decimal point followed by 34 zeros and then a 1. It is so small that a proton, which is already unimaginably tiny, is a billion times larger. At these scales, the smooth fabric of space-time that general relativity describes would break down. Space-time itself would become quantum. It would no longer be a continuous surface. It would be a foam, a jumble of tiny bubbles and loops constantly fluctuating. This is the quantum foam.
This is where the two theories must meet, and this is where our understanding collapses. So, what do we do? Physicists have been working on this problem for decades. Two approaches have emerged as the leading candidates for a theory of quantum gravity. They are string theory and loop quantum gravity. String theory began in the late 1960s as an attempt to understand the strong nuclear force. Physicists were trying to describe the behavior of quarks, the particles that make up protons and neutrons. They found that a mathematical model based on vibrating strings worked remarkably well. But then they made a strange discovery. The equations predicted a particle that had never been observed, a particle with zero mass and a spin of 2. This was in fact the graviton, the hypothetical particle that would carry the force of gravity if gravity were quantized. String theory, which had started as a theory of the strong force, had accidentally included gravity. This was a stunning revelation. For the first time, there was a framework that could potentially unite quantum mechanics and gravity. The idea is simple in concept, even if the math is incredibly complex. Instead of point particles, the fundamental objects of the universe are tiny, one-dimensional strings. These strings vibrate at different frequencies, and just like a guitar string can produce different notes, the different vibration modes of these strings correspond to different particles. One mode gives you a photon, another gives you an electron, another gives you a graviton. All the particles of the standard model are simply different vibrations of the same fundamental string. This is elegant. This is beautiful. It unites all the particles and forces of nature into a single framework. But string theory has a price. For the math to work consistently, the strings must exist in more than the 3 dimensions of space that we experience.
The original version of string theory required 26 dimensions. Later versions, which incorporated supersymmetry, brought that number down to 10. In some versions, it is 11. These extra dimensions are not just arbitrary additions. They are necessary for the theory to be mathematically consistent. So, where are these extra dimensions?
The answer is that they are curled up, compactified into shapes so small that we cannot detect them. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but up close, you can see that it has a second dimension, the circumference of the hose. The extra dimensions of string theory are like that, curled up at the Planck scale, too small for us to observe directly. This is one of the reasons string theory is so difficult to test. The energy scales at which the stringy nature of particles would become apparent are far beyond anything we can achieve with current particle accelerators. We would need a machine as large as the solar system to probe these scales. So, string theory, for now, remains a mathematical framework, not a confirmed theory. But that does not mean it is useless. String theory has produced important insights into black holes and the nature of information. It has inspired new mathematics. It has given physicists a way to think about the unification of forces that they did not have before. It is a work in progress. And even if it is not the final answer, it has moved us closer to it. The other major approach is loop quantum gravity. This theory takes a completely different philosophical approach. Instead of starting with particles and adding gravity, loop quantum gravity starts with gravity and tries to quantize it. It is a theory of space-time itself. The idea is that space-time is not a continuous fabric. It is made of discrete pieces, like a fabric woven from tiny loops. These loops are not in space. They are space. They are the fundamental building blocks of the universe. The geometry of space-time emerges from the relationships between these loops. Loop quantum gravity does not require extra dimensions. It works in 3 dimensions of space and 1 of time. It is more conservative in that sense, but it is also more difficult to connect to the rest of physics. It does not naturally include the other forces of nature. It is a theory of gravity, and gravity alone. To create a complete theory of everything, loop quantum gravity must be combined with other frameworks. Both string theory and loop quantum gravity are still incomplete. Neither has made a definitive prediction that can be tested by experiment. Neither is universally accepted. The problem of quantum gravity remains unsolved. But that does not mean we are stuck. We have learned an enormous amount. We understand the nature of the problem. We have developed powerful mathematical tools to address it. We have made progress, even if we have not reached the finish line. And there is another reason to be optimistic. The universe itself is a laboratory. We can observe black holes, the most extreme gravitational environments in the cosmos. We can observe the cosmic microwave background, the afterglow of the Big Bang. We can observe the behavior of particles at the highest energies. Each of these observations is a test of our theories. Each observation provides new data, new clues. And sometimes, the data brings surprises. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating. This was completely unexpected. Everyone had assumed that gravity would slow down the expansion. But instead, something is pushing the universe apart faster and faster. We call this something dark energy. It is a placeholder name. It means we do not know what it is. It is not matter. It is not radiation. It is something else. Something that permeates all of space and exerts a negative pressure, pushing things apart. Dark energy makes up about 68% of the total energy of the universe. It is the dominant component of the cosmos, and we have no idea what it is. There is also dark matter. When astronomers measure the rotation of galaxies, they find that the stars are moving too fast. They should fly apart, but they do not. Something is holding them together, something invisible, something that does not emit light. We call this dark matter. It makes up about 27% of the universe. It is not made of atoms. It is not any of the particles we know. It is something else. something we have not yet detected directly. If you add it all up, the ordinary matter that makes up you and me and the stars and planets is only about 5% of the universe. Everything else is dark matter and dark energy. We have no idea what most of the universe is made of.
This is humbling. After centuries of progress, after the triumphs of Newton and Einstein and the quantum revolution, we find ourselves in a universe that is mostly unknown. The equations that work so well for describing the visible parts of the cosmos fail when we try to apply them to the dark parts. We are, in a very real sense, standing at the edge of knowledge, looking out into the unknown. But this is not a reason for despair. It is a reason for excitement. The greatest discoveries in physics have always come from confronting the unknown. The ultraviolet catastrophe led to quantum mechanics. The Michelson-Morley experiment led to relativity. The anomalies in the orbit of Mercury led to general relativity. The unknown is not our enemy. It is our guide. It shows us where to look next. The dark matter and dark energy are not failures of physics. They are invitations. They are the next great mystery to be solved.
And somewhere, right now, there is a young physicist, maybe a graduate student, maybe a postdoctoral researcher, who is thinking about these problems, who is turning them over in their mind, who is searching for the key. And one day, that key will be found, and the unknown will become known. The same is true for the problem of quantum gravity. It is the most difficult problem in physics, but it is not unsolvable. The human mind has solved difficult problems before. It will solve this one too. And when it does, the solution will be beautiful. It will be simple and elegant. It will be something that, once you understand it, seems obvious. It will be the next step in the great dance of understanding. What will this solution look like? Nobody knows, but we can make some guesses. It will probably unite the forces of nature into a single framework. It will probably reveal that space and time are not fundamental, but emergent, arising from something deeper.
It will probably have something to say about the nature of information and consciousness. It will probably change our understanding of reality in ways we cannot yet imagine. But that is the future. For now, we are here, at the edge of knowledge, looking out into the unknown. And there is something beautiful about that. There is something beautiful about the unknown. It means we are not finished. It means there is still work to do. It means the dance is not over. It is just getting started. We have come a long way in this journey. We started with the simple question, what is motion? We have seen that motion is not what we thought. It is not a change of position in space. It is something deeper. It is the fundamental property of the universe. Everything moves, everything changes, everything evolves. And we are part of that movement, that change, that evolution. We are not separate from the universe. We are part of it. The atoms in our bodies were forged in the hearts of stars.
The molecules in our lungs were breathed by dinosaurs. The water in our cells was once part of the ocean. We are connected to everything. We are the universe, experiencing itself. And the dance continues. It continues in the stars, burning and fusing. It continues in the galaxies, spinning and colliding. It continues in the quantum foam, seething and fluctuating. It continues in the dark energy, pushing the cosmos apart. It continues in you, in every heartbeat, in every breath, in every thought. You are not just a spectator. You are not just a passive observer. You are an active participant. You are part of the dance. Every time you ask a question, you are part of the dance. Every time you seek an answer, you are part of the dance. Every time you wonder, you are part of the dance. And the dance goes on. It has been going on for 14 billion years, since the Big Bang. It will go on for billions of years more, until the last stars burn out and the universe reaches its final state. But even then, the dance will continue. Because even in heat death, even in the cold and the dark, there will still be motion. There will still be quantum fluctuations. There will still be change. The dance never stops. It cannot stop, because motion is the fundamental property of the universe. It is what the universe is. So, when you lie here now, feeling the stillness of your body, remember, you are still moving. Your atoms are vibrating. Your electrons are spinning. Your molecules are jostling. You are part of the great dance. You have always been part of it. You will always be part of it. And that is the most beautiful thing to know. That we are not separate. That we are not alone. That we are part of something greater. That we are part of the universe. That we are part of the motion. That we are part of the dance. So, rest now. Let the dance continue without you. You will join it again in the morning. For now, let your thoughts settle. Let your breathing slow.
Let your body relax. And let the gentle rhythm of the universe carry you into the quiet depths of sleep. The story of motion is the story of everything. It is the story of the stars and the planets. It is the story of the atoms and the particles. It is the story of life and death and everything in between. It is the story of you. And it is a story that never ends. It goes on, forever and ever, a dance without end, a movement without pause, a universe in motion. And you are part of it, always. So, good night, sleep well, and know that you are part of the greatest story ever told, the story of the universe, the story of motion, the story of everything.